Muted, okay. Hello, everybody. Welcome to Friday, end of the week. Let the camera try to actually find my face instead of the middle of my chest. You can see in the homework that it's kind of half circuits, half magnetic interactions, mainly relating to the two equations that I discussed with the cross product on Wednesday, but there's a couple other ideas that came in, either directional ideas and some of those conceptual questions that were about one other equation about if you have a long straight wire, what kind of magnetic field do you get around or nearby the wire? And that was relevant to a couple conceptual questions. And I think also came up in the question in chapter 32 that had two circuits drawn kind of side by side, and they asked, like, what is the force between this part of one circuit and that part of the other circuit? Let's see. It's probably more in the way than anything. So I want to spend maybe half the time today putting out a couple magnetism concepts and equations, elaborating off of the ones already introduced, especially, and then also maybe just having some equipment out and kind of showing you what it might look like to have in mind, because we'll see descriptions of things. Kind of compasses. I should have brought a wire, just a plain old wire. So there's, kind of do it here on the doc cam. So eventually, maybe not totally today, but a little bit today. Zoom out. Is that as far as it goes? Oh, okay. That's as far as it goes. Zoom back. It's got to go further out than that. Okay. Now back up. Okay. Okay. I feel like it should be able to get further away than that. So here's a couple items that we'll probably refer to pretty often. And I wish I had remembered to bring one more. I don't know if you can see this, but we've got things like some of our favorite objects that give rise to magnetic fields, of course, would be like a bar magnet. I should put a bar magnet in there. So do you know what the magnetic field is of a bar magnet? We've talked about the shape of it. We don't really have equations for that one. We did take some measurements of the strength of the magnetic field off the axis of the bar magnet yesterday, but that's really good. We could do some approximations and kind of have a number that describes the strength of the bar magnet, but in general, we'll probably just kind of concern ourselves with knowing the dipole pattern of the magnetic field shape. And maybe we'll have flat or very thin circular coils or coils. I have another one that's rectangular over here that I think over here that maybe we'll do some questions with. A thin circular coil, and we had an equation, of course, we used quite a bit, or maybe you will use quite a bit, really yesterday's lab, along the axis of this coil. Not everywhere, but on the axis at least. And then we might have things that look like this, where it's a coil, there's tons and tons of wrappings here. And there's, there's spots to kind of connect the voltage or connect some wires here and there. I can plug some I can plug some leads in here, but it's a lot of wrappings kind of equally spaced along a clear length. So we'll have one, and then the other one that I wish I had is just if I would have just brought a wire and just had like a long straight wire. So those are kind of three of the main ones that are mentioned in the chapter summary for chapter 32. What is the magnetic field shape and equation in the vicinity of a long straight wire carrying current I? What is the magnetic field shape and equation for the magnetic field in the vicinity maybe of a circular current loop, especially on the axis? And then something like this, the long coils kind of regularly spaced. There's lots of windings in there. This one has 800 wrappings spread out over, we can measure that. I can't remember the length. I think it's like 4 centimeters. And this one has 200 wrappings, also equally spaced out over the same length of 4 centimeters. I think 4 centimeters. And something like this or this or this, the main, we could talk about a variety of things, but the main question we'll be curious about is what is the magnetic field like inside there? And then especially like deep inside, kind of like pretty far from the edges, as we often do with some objects that are fairly large, and we're going to kind of pretend they're really, really large. So, and an object like this is usually called a solenoid. So what is the magnetic field direction and equation inside of a solenoid? And it ends up depending on, how much current is flowing around all those wrappings is always going to be relevant. The number of wrappings is pretty much always going to be relevant. If you have multiple wrappings, just multiply by the number essentially. And then the shape. So we might want to know here things like what's this length? What's this length? Maybe we want to know like what's the radius of that circle. Here, we saw in this, we want to know where we are on the axis and what's the radius of the circle. And for a long straight wire, what would the main kind of measurement perhaps of interest be? How far away are you from the long straight wire? Are you standing, underneath a power line that's 10 feet above your head carrying 12 amps, or are you standing underneath a power line 35 feet above your head that's carrying 12 amps? There's a different magnetic field, not too surprisingly, for that. And maybe not too surprisingly, it's weaker the further you are away from the wire. So some of that stuff. And what we've mainly seen so far, or one takeaway thought so far, is we had an equation for this, which we'll, I think, derive maybe by Monday. But this guy, and the bar magnet, and this guy all have very similar shape magnetic fields. They could all kind of be called dipoles. They could all be called magnets or electromagnets. And for this guy, and this guy, we'd want to know which way is the current circulating. And then if it's circulating in certain orientation, you curve your fingers in the direction of that curving, circulating current. And your thumb will point, and you could interpret the direction of the right hand, thumb of your right hand a couple ways. You could say this is going to be like the North Pole end of it. You could also interpret it as saying the magnetic field shoots down the axis and wraps back around on the outside, and the thumb is showing you which way the magnetic field points all the way along the axis. So all of these guys generally have a very similar shape magnetic field, which is kind of like away from us inside of the loops and then circulating back around towards us and then through and towards us in all directions. And like the longer you make this, the longer region you get where like the magnetic field lines are just kind of uniformly spaced shooting down the axis before they start to spray out the end. And if they're fairly uniformly spaced along here, what does that kind of mean about the strength of the magnetic field? Pretty much a uniform strength magnetic field over a pretty large region or volume of space kind of inside of the solenoid. So this guy is kind of our, it's our favorite way to create a uniform magnetic field. Like if I had to go into the lab and create a magnetic field that's about the same strength and direction everywhere over a certain pocket of space, so I could do an experiment or take some measurements or carry out an experiment, most likely, this would be kind of the go-to way to do it. I'd maybe use bigger wrappings because I'd want to have some space in here to do my whole experiment. But in the vicinity inside there, we get a pretty uniform magnetic field. In one direction, it's either down the axis that way for one orientation of current, or it's down the axis the other way for the other orientation, like clockwise, counterclockwise, current. And it'd be nice to know how to make a fairly uniform magnetic field. Another way you could get a fairly uniform magnetic field instead of using current is, I'm going to hold this guy up. Have this guy, and in the space between these poles here, it'd be fairly uniform in there. What is so that's magnetism. Just for comparison, what's a way to get a nice uniform electric field? Because the solenoid, which I think is kind of related to the French word for coil, is our go-to way to make a uniform magnetic field. There's a formula of how strong it is, but it's the same strength everywhere. What's kind of a good way to get a uniform electric field? Parallel plate capacitor. Inside, you get a fairly uniform electric field, and outside it's pretty much zero. And almost the exact same thing is true for this guy. Inside here, there's going to be a strong uniform magnetic field, and outside, it's going to be very weak, close to zero. And then if you get near the ends, both of those statements start to break down a little bit. And you can almost kind of think of it as, like if you had a North Pole and a South Pole, big flat North Pole face and big flat South Pole face close together, that's kind of like a big negative plate and a big positive plate close together, and across the gap, you get a pretty uniform electric field pointing from positive charge to negative charge. So across the gap, you get a pretty smooth, uniform magnetic field from north to south. Not around here. This is going to be a curving kind of magnetic field around all this stuff, but in this gap here, pretty good. We'll see some other versions of that. So those are sources. I'm going to put that in the category. Those are sources of the magnetic field. Those are kind of help us think through questions like, if I'm given object A, how strong is the magnetic field at a nearby location? Equations that would basically be like B equals equations. An equation that I want to pick up to calculate B in Tesla. The other half of it, which I think is more what today's homework is about, because I started talking about first, is what about equations that take in B as an input and want to ask you to calculate what is the force on the charge? What's the force on the wire? Will it want to point this way, or will it want to rotate and will it want to pivot into a different orientation, like a torque or a force moment? So I'm just going to kind of go through one or two examples of that, and we'll see if that comes up in the homework. White blank sheets. Okay, so I kind of call this the force law, I think. And anytime you're using magnetic field, either as an input or an output of an equation, we're going to have right-hand rules across products somewhere running around. And that means it's very, very 3D. You can make really interesting electric physics arrangements that are 1D or 2D. If you try to make a magnetic arrangement 1D or 2D, there's no effect. The answer is 0, because it's like you're kind of crossing two vectors that are not oriented in the right ways, and you get kind of 0 as the result. So if you make it, let me say this, if you try to make it 1D, the answer is 0. If you try to make it 2D, you'll end up with it actually being 3D, because the other quantity that you're interested in will probably be perpendicular to the 2D plane that you started out in. And if you make it 1D, then it's 0. That's what I probably should have said. So force on a moving charge. If the charge is not moving or is totally stationary or moving very slowly, it might feel an electric force, but it won't need to feel much of a magnetic force. But now let's have it moving at a decent enough speed, or it's in a strong magnetic field. So this is a moving charge, and this is the magnetic field it's inside of, or the magnetic field at its current location. And remember, whenever we're doing kind of field thinking, we're thinking there's some source nearby. It's better. There's some source that's giving rise to the B. But for right now, we're not going to concern ourselves with what the source is. We're just going to say there is this magnetic field strength and direction present. What effects will it have? How will I know if there is a magnetic field present? How will I know how strong it is? How will I know if it points east or north or south? Well, one little experiment you could do is, if you want to know if there's a magnetic field present, put a little charge down, know the amount of charge you have, fire it a certain direction, and see if it feels a force. And then you could kind of say, well, I know the charge and I know the velocity vector and magnitude I gave the charge. I observed or measured a certain force direction or vector, and I can work out some information about B. It turns out though, if you just did one experiment, let's say you just did this experiment, you fire the object east, it's positive charge. You fire the object east and you observe it to feel a certain strength northward magnetic force. From that, you'll be able to learn some information about B, but you won't be able to learn all the information about B. Because it turns out there's more than one vector you can cross with a given vector to get the same output. You know what I mean? Like if this is a normal algebra equation, it'd be something like 8 equals 2 times x. Well, there's only one answer for x, 8 divided by 2. But if you're saying vector equals vector of magnitude 8 north equals vector of magnitude 2 east cross unknown vector, you'll be able to learn some of the components of the unknown vector, but not all of it from just that experiment. And then if you did 2 experiments and kind of fired the object again at that location in another direction, then you can kind of pick up all the information. So let's just kind of imagine this. Let's say Q is, we'll have it be our favorite guy or one of our favorite charges, proton. And let's say the velocity vector, I'll just kind of draw it over here, Q, which is positive, and I'm going to fire it this way. And I'm going to say, this is kind of my experiment. I'm trying to determine, is there a magnetic field at point Q, or at this little dot? So I put a charge there. I fire in a certain direction, or I conceptually imagine that. And let's say my response force is this response force. And I'll put some numbers to this. So let's say the output is, I wanted to give the velocity first. The velocity will be 8 times 10 to the 6th meters per second. And then let's say the force you get is north. Oh, sorry, I'm going to write the words in here, east. So I'm going to kind of put this here, east, north, west, south. Okay, and then let's say the force you get is 3.84 times 10 to the minus 12 newtons north. So then the question is, I'm just going to word this intentionally, what can we conclude about B at that location? What can we conclude? What can we calculate? What can we know for sure? What maybe can't we know for sure? What can we conclude about B at the location the experiment was done? So we'll just think about this. So, okay. So you could do this, and in general, I'm going to kind of do this twice, or I'm going to kind of do it twice. In general, you could do this kind of using unit vector notation, and you could kind of try to work out what are the components of B, or you could kind of do it using kind of magnitude and direction thinking. What's the direction of a cross product? Right-hand rule gives you the direction of the cross product, and then you multiply by Q, which might be negative, but isn't here, to get the direction of FM. And then what's the magnitude of a cross product? What's the magnitude of the cross product of 2 vectors? It's the first vector's magnitude times the second vector's magnitude times sine of the angle between them. It's like the magnitude of one vector times the component of the other vector perpendicular to the original or to the first vector, one of the vectors. And to get the perpendicular component, that'll be related to sine of the angle between them. So another way to, write this would be if we had V pointing this way and we had B pointing this way, and then you see an angle between them. And in doing this, you kind of would mainly want to draw the vectors kind of, or visualize vectors tail to tail. We're never going to add V and B because they're different quantities. So we never have to put them tip to tail, but we might want to just kind of draw them from a common origin. So what is the magnitude of this? The magnitude of the output is, and then there'd be a charge here. So I guess we should take the absolute value of the charge, and then we'd have V, and V means the magnitude of the velocity vector, and then we'd have B, the magnitude of the magnetic field it's sitting in, and then you'd have sine of theta. Okay, and B is intrinsically positive, it's length of a vector, B is length of a vector, we're trying to get the length of a vector, we'll take the absolute value of Q, and sine of theta will range from what to what? Yeah, if they're parallel vectors, sine of 0 is 0, sine of 20 some small decimal, you get up to sine of 90 is 1, and then you're dropping back down towards 0 for anti-parallel V and B. Okay, so you could do it this way, and then what's the direction that would go with this? The direction would be determined via right-hand rule. And in this case, what direction would the force be, for what I've drawn here? Assuming it's a positive charge, V cross B points in the out of the page direction, and if it's positive charge, up out of the page. So you might say something like V and B lie in the XY plane. They kind of somehow together occupy the I hat, J hat kind of plane, and the output has to be perpendicular to both ends. How many directions are there in 3D space that are perpendicular to V? Lots. How many directions in 3D space are perpendicular to B? Lots. How many directions in 3D space are perpendicular to both V and B? 2, and they're opposites, right? And then we have to break the tie. So like everyone agrees, okay, the force doesn't lie in this plane. Everyone says, well, I know it doesn't lie in this plane. It's either at me, like perpendicular plane this way, it's away from me. And what we have to do is we have to, every time we come to one of those decisions, we have to break the tie the same way we broke all the other ties and all the future ties. So we've decided to break the ties using right-hand rule. There's nothing intrinsically right-handed about magnetism, but we do it this way. So we do things like, if I draw the x-axis to the right, and I draw the y-axis this way, we've kind of made a standard choice for which way the z-axis is going to point. We've kind of decided the z-axis is going to point at us. And that's kind of been hardwired into things like I hat cross J hat is K hat. And right-hand rule's in there. Because if we draw the z-axis pointing at us, a lot of people would call that a right-handed coordinate system. If we draw the z-axis pointing away from it, you might call that a left-handed coordinate system. But the vectors don't really care how you draw the axes. And we'll come back around to that idea. I'll just kind of give you a little preview right now. If you're given the magnetic field direction, somebody has already had to make this break the tie choice. And so when they give you that the magnetic field points the way I drew the arrow, it's like you have to accept with it that, okay, I have to use the information you gave me in accordance with the implied convention that comes with the information. The real core thing to tell me that wouldn't depend on convention would be to say, okay, instead of telling me B, tell me where the charges are that are moving that's giving rise to B. And if you told me that stuff, then I could either do the whole problem start to finish using right-hand rule, or I could do the whole problem start to finish using left-hand rule, and I'd come to the same conclusion about which way this positive charge is going to feel a force. So we'll maybe see examples of that eventually. Okay, so what can we conclude about this particular example here? So let's kind of do this kind of just like magnitude and direction wave right now. Let's say there's 3 possible components to consider. Can we conclude anything about the east-west component of B, purple B? Can we conclude anything about the north-south component of purple vector B? And can we conclude anything about the, vertically upward out of the page, vertically downward into the page component of vector B based on this little experiment. So let's start with kind of 3 questions. Let's say question 1, can we conclude anything about the up to down, like perpendicular to the page component of magnetic field from this little experiment? We're sure it's up out of the page. We're sure it's down into the page. We're sure it's 0, or we don't know. I'm kind of imagining those would be the 4 possibilities. It's got to have a magnetic field out of the page. It's got to have a magnetic field into the page. It must have 0 magnetic field perpendicular to the page. Or, you know what, I'm not 100% sure because I think there's more than one possibility here. Up to down, we can determine one or the other. One of them is going to be consistent with right-hand rule, I think, and one of them will be inconsistent with right-hand rule. So is this out of the page or into the page for B? If I try out of the page, I think my hand would give me a thumb pointing down. I know you can't quite see that. Yes, maybe try it out. If I considered what if there were a magnetic field pointing into the room, I get a force on a positive charge southward, and it's got northward force. But if I try a magnetic field pointing towards the back wall of the room into the page, then I would do this, and I would get something consistent with this. Could there be 0? It can't be 0, otherwise you wouldn't have a force northward or southward. So I think we can say up, down, question mark? And the answer would be, it's going to have to be down. Yeah? Down meaning away from us, away from the viewer, and we could also use the symbol X, meaning away from the viewer. What about north-south? And now here, I don't mean magnetically north-south, I mean like truly geographically north-south. Can we conclude anything about the north-south component of magnetic field? Possible components, I don't know why I can't zoom this back further. Components of B. It seems to be really zoomed in today. That's better. Now it just let go and it went much further. Okay, that's better. And then 3 will be, 3 will be east-west component. What about north-south? This is the easiest question on the, to my mind, this is the easiest of the 3. Before worrying about right-hand rule to break the ties, what's the general fact about a cross product? The output is perpendicular to both inputs. So if the output occupies either north or south, in this case north, or that would mean what about the magnetic field? It must not have any north-south component. And also that's kind of built into this that I chose F, M, and V to be perpendicular. If I had said, here's my experiment, I fired the object east, and let's say I just claimed that it felt a force, 70 degrees north of east. That wouldn't possibly be correct. Something's wrong. You can't possibly have a charge moving east feel a magnetic force 70 degrees off that X. It's got to be perpendicular. So that's working for F, M, and V. But from this, I know that this has to be 0 because FM is perpendicular to B. Okay, and what about east-west? We have no idea about the east-west component of magnetic field. Why not?
It could be anywhere in the east-west plane, and the force would still be perpendicular.
And are you kind of imagining explaining that to someone via right-hand rule, via components? And that's true. That's true.
I mean, kind of right-hand rule, just because like the definition of the cross product, if you like set up a plane, like you said, like east-west was the x-axis, it could be anywhere in the x-plane. The force would still be perpendicular.
Something like that. You could explain that in various ways. That's definitely true. If you do a cross product what is the cross product? Here's maybe another way to get the same idea across. You could try right-hand rule. Try imagining a down into the page, but slightly eastward vector. I think you should get a force that points north. Try imagining a straight down into the page with no east or west vector, or straight into the page with a little bit of west. All of those will give you a right-hand rule with FM pointing due north. So you could say something like that. You could do it with components. I think we will in a second. Or you could say, what's the whole point of the cross product? What's the kind of geometric idea? All that matters is how perpendicular these two vectors are. So any parallel component of B, what do I mean by a parallel component of B? Any component of B parallel to the velocity feels no force anyways. Only components of B perpendicular to V, if you want to switch that around, you can. Only components of V perpendicular to B, two ways saying the same thing, matter. Now what if they ask this question? The way they might get around this question in a story problem is they might say, what is the weakest magnetic field that could possibly exist there? And that would be to have the magnetic field point in the optimal direction for most bang for your buck. And that would be that the magnetic field being perpendicular to the other vector it would be. We don't know. And let's go to the one that we know is down. How strong is the downward component? Well, now if we have numbers, we could kind of say how strong the downward component is. And basically, if we do this, QV, all of Q, well, that's a scalar, all of V times the perpendicular component of V equals all of F. So from that, we could kind of divide those guys and say the perpendicular component kind of down here, B perpendicular, which in this case is going to be B, the downward component basically. How strong downward? That'll be the magnetic force divided by QV. And now I'm intentionally not putting vectors in those to mean magnitudes of those guys. So 3.84 times 10 to the minus 12 newtons and 1.60 10 to the minus 19 coulombs and 8.00 10 to the 6th meters per second. And I'm just going to say this is the minimum strength magnetic field that could possibly be there. And I think if we type those in, 3.84 e to the minus 12 divided by 1.60 e to the minus 19 times 8.00 E6. And I got 3 Tesla. So that's kind of our answer. And let's just do it again using unit vectors. Because you can do this pretty nicely if you're, your unit vectors. So can we write V in vector notation? Can we write FM in unit vector notation and then just kind of set up a cross product? I think I'll kind of do that right down here. So FM is 3.84 times 10 to the minus 12 newtons J hat. If I were to kind of have X, Y, and then Z will stick out into the page like that. So that's that guy. And then we've got a scalar, 1.60 times 10 to the minus 19 coulombs. That's a scalar. It's not a good black pen. Okay, and then we got V, which is going to be in the I hat, and it's got a certain magnitude of 8 times 10 to the 6th meters per second I hat. And then I'm just going to kind of do cross, just pretend that continues from the last line. And then I'm just going to, for right now, write BX I hat plus BY J hat plus BZ K hat. Like I want to learn all the components, so I'll just kind of let them all be in there. And what happens when you do this cross product? Right off, one of these 3 B components drops out immediately. right? Which one drops out immediately? I hat cross I hat is 0. So whether there's a positive, negative, big, strong, or 0 Bx, it's not going to survive this cross product anyhow. All that's going to survive are components perpendicular to, oh, I didn't put a hat, I hat. So if we do the cross product on the right, I'll just leave the 1.6 out front. 1.6, 10 to the minus 19 coulombs. And then what would you get here? I'll put the 8 times 10 to the 6th meters per second. Those are scalars. And then what do I get in terms of components? I cross I is 0. I cross j is k. So I get plus by k hat. Yeah. And then I cross k is negative j. So I get a minus bz j hat. And I just want to equate this with what's on this side, which is 3.84 times 10 to the minus 12 newtons, all in the j hat. So what do we conclude? The only way two vectors can be equal is if each component's equal. So what do I conclude about by? 0. Right? There's no k hat on the left, so there's no k hat on the right, so this coefficient is 0. And what do I learn about bz? You know, things can come out negative essentially, and you can just kind of equate the j hats, drop the j hat, and then just kind of solve that equation. And I think you'll get that bz is negative force over qv, and the negative would indicate the downward guy. So I think we get, you know, we solve when we learn two things. By is 0, and we learn bz is negative. The number up above was 3 Tesla. But what happened along the way? We lost a guy along the way. We lost bx, so we don't know what bx is. This would be a lot like saying, what would can anyone kind of imagine a little bit this kind of question here? Like, what would the force and moment, like, version of this kind of be? Like, we know the first component, we know the first position of the cross product, and in the moment calculation, that would be radius. So like, we know where a force is applied to the object. We don't know the force, which in that scenario plays the second role of the cross product, but we do know the resulting moment. And then we're trying to figure out how strong and in what direction did somebody apply a force to make the object feel this torque. Maybe like to open the door. I'm kind of thinking of the door right over there because that's something on hinges. This would be a little bit, can't really see the door back there. This would be a little bit like saying somebody applies a force a certain distance due east of a pivot. And in response, the object kind of swings in a certain direction with a certain moment. What force did the person apply at that location east of the pivot? And we could figure out some things, but not other things. And this is not the force. Actually, the door's swinging that way, but like, let's say you needed to open the door, and it takes a certain amount of torque to open the door. And let's say we've decided you're going to apply your force, and you probably can't see this well. Let's say I'm going to apply my force a certain distance from the hinges. I'm going to apply my force 0.8 meters from the hinges. There's a minimum force that'll get that done. It'll like hold the door from like swinging or open the door. There's a minimum force, but I can apply a much stronger force at a bad angle to get the same job done. That kind of makes sense. Like, I should pull the door kind of straight this way to get it down with the weak force, but I could pull this way really, really strongly. And I'm putting a lot more into it right now than here to get it done, because I'm just changing what the component of my force is right back at the hinges or away from the hinges, which isn't going to lead to any rotation anyhow. So it's possibly there, but there's 0 torque associated with one of those components. So in this case, there'd be 0 force associated with one of those components. Okay. So just some thoughts there. So, if you know the two inputs, you can calculate the one and only ambiguous output. But if you know the output and one input, you learn two of the three components of the other input. But what can we do to kind of fill in the other information? Just do another experiment and fire this charge in a different direction. That's not east or west, and then you'll learn that extra component. Yeah. Dot product issues will only tell you one of the components. If you dot with V, you're only going to learn about the I hat component of the other vector. Okay, let's draw a couple pictures to give you an idea of the answer to one of the idea behind one of the questions in this week's homework, and then we'll just look at homework. So I want to imagine thinking about this equation here, Fm equals QV cross B. I want to imagine kind of one of our favorite scenarios. So what if the magnetic field is uniform? What if you have a pocket of space where it's the same strength and same direction magnetic field everywhere? And then let's say this could maybe be the initial moment. So you put the proton right there, you put the positive charge right there and fire it to the right. But what's it going to do a second later? So let's say, I'll redraw it, but this would be like the magnetic field pointing in, we decided. What's going to happen to this guy a second later? If there's no other forces besides the magnetic force, what's he going to do? He's going to accelerate in the direction of the force, and he's going to no longer be heading due east a little bit later. He's going to be heading a little bit north of east. And if the magnetic field is the same, when he travels a little bit, he moves like a couple centimeters. He moves a couple centimeters north and east, and now he's traveling that way. If the magnetic field is the same at the new location, it's still pointing in. And then what happens, and then what happens. So I'm going to kind of go through that scenario, but I'm going to change the 3D view to help us out a little bit here. So what about a charged particle moving in a really nice magnetic field, in a uniform magnetic field? So B is a constant vector, constant magnitude, constant direction at all points that are relevant for the next couple minutes here. So I'm going to set this up, and I'm going to do the easy scenario where the object's going to start out moving perpendicular to B. And I just want to think to myself, which way I want to write this. So I'm going to show the object starts out right here. The object starts out right here, and it's going to move this way, very much like what I drew previously. But the magnetic field is going to be perpendicular to the page. So it's a nice uniform magnetic field, and I'm just going to represent it with a bunch of dots, like an army of equally spaced dots. So this is the magnetic field, and just to be clear, that means the magnetic field points out, right? That's kind of the dot notation. The X is the in away from the viewer notation. The dot is the out at the viewer notation. And I'm just going to kind of do a little bit more of this to kind of say, like, this is everywhere that we need to concern ourselves with. It never kind of gets outside of this uniform strength. And you should kind of draw them about equally spaced to represent equal strength. So we'll put numbers to this in a second. Maybe we'll do about the same numbers we had before. 3 Tesla, and the velocity was the same number as before, which is 8 times 10 to the 6th meters per second. And the Q will be the same Q, but now we're also going to at some point want to know what's the mass of this guy. Because if he's feeling a non-zero force, then we have to take that force and divide by mass to get acceleration. So if we want to kind of track him for a couple seconds, we're going to need to know, is he a bowling ball with this much charge, or is he a little ping pong ball with a certain amount of charge? So let's just make him a proton. So this is 1.67 times 10 to the minus 27 kilograms. And this is the same one we had before, 1.60 times 10 to the minus 19 coulombs. Okay, so first of all, what direction will he feel his force right now? So we do right-hand rule, and and what direction do we get? I can't get my hand there. I think down the page. Yeah. V, curl my fingers towards the viewer in the dot direction at the viewer is down the page. So if I do right-hand rule right off the bat, I get maybe this vector right here. And of course, that's perpendicular, right? It's in the plane of the page perpendicular to green, and it's either directly north or south. It's directly south to be perpendicular to purple. Right-hand rule breaks the tie and says directly south. So where is this guy going to be just a little bit later? He's going to have curved to maybe, let's say, right about here. So we've kind of unfrozen the picture in time and let it play out for a tenth of a second and refrozen it. Okay, couple thoughts. How fast is he moving now? Short interval of time, but he's feeling a non-zero force, right? Is he traveling faster at the new moment than before, slower at the new moment than before, or the same speed as at the new moment as at the prior moment? This is more of a force F equals ma, vectors, acceleration, velocity question. This is not so much a magnetic physics question. Does he speed up, slow down, or stay the same speed over a short little blip of time? Speed up, slow down, or stay the same speed? Everyone can vote and just kind of yell it out in the chat. On the count of three, speed up, slow down, or stay the same, just yell it. 1, 2, 3. Take a shot, take a shot. Take a guess.
Stay the same.
Stay the same.
I think it's gonna slow down. I mean, are we just talking about the magnitude or like the speed and like a specific direction?
The magnitude is kind of what I had in mind.
Then it'll stay the same.
It's same. So of course, acceleration is parallel to force. If the acceleration is perpendicular to the velocity, you only curve, you don't speed up or slow down. What would have to be true about the FM direction, which isn't true here, but what would have to be true to make it speed up? There'd have to be a component of FM eastward or something like that. Or if there was a component of FM westward, then you might slow down. So we often call something like this, anyways, so this is just going to curve you. This is just going to curve you, which means you're going to kind of curve and you're no longer heading in the direction you were previously, but you're still, so I'm going to try to draw the vector about the same length. You're traveling at the, that was a little too far. You're traveling at the same speed. Maybe I should call this V1 and V2, but they're the same magnitude. And then, of course, we're saying it's a uniform magnetic field. So at the new location, it's the same strength and direction V. So now what do we get if we do right-hand rule? Now the new guy feels a new force. And the new force has to be perpendicular to the new V. So the first magnetic force is like that. The next magnetic force is about like that. And how does the magnitude of the new magnetic force compare to the old one? Same. So what happens next? Kind of come into about here, and now you're heading, that way, V3. And so what happens if you kind of unfreeze and just watch this play out over time? What's the particle going to do? Now it's a bad circle, but it's going to end up following a circular path. He's going to end up revisiting where he started from after some amount of time. And why is it circular? That's a good setup for circular motion. A force always points inward, and you kind of extend these out. The center of the circle would kind of be the point at, I didn't do a very good job there, but like all these vectors would point at the center of the circle. We might call it centripetal acceleration, centripetal force. And this is all saying a couple things. The magnetic field is uniform, and there's no other forces that we're wondering about. This is the only force causing, affecting the object. And if we put this together, you're going to get uniform circular motion. Uniform meaning constant speed. Now, contrast that to what happens if you fire a charged particle in a uniform electric field. Let's say the electric field points downward, and you fire a positive charge to the right. It follows a parabolic path curving downward, and it speeds up, right? Speeds up, speeds up, speeds up, and follows a parabola. This never speeds up or slows down. In fact, can a magnetic force ever speed up a charged particle or slow down a charged particle? Never, because it's always going to apply a force perpendicular to the velocity, kind of by the hardwired format of the force law, which means all it can do is curve it. Not curve and speed it up, which is good for gravity can curve it, gravity can speed it up, gravity can slow it down, but not this guy. Uniform circular motion, and we might do something like this. We might equate the force. And remember, I set it up so this is all very nice. So the magnitude of the force, I think I'm going to do this as magnitude. On the one hand, that's MA, right? And then on the other hand, that is QVB sine theta. But in this case, the sine theta is sine of 90, which equals 1 because I arranged them at the start to be perpendicular. So just kind of return us putting that in there. And then what could we say about MA? What's the equation for centripetal acceleration? mv squared over r. If you want to know something about the size of this circle, how large of a circle will it be bent into? Well, you're going to have to tell me, how big of a bowling ball it is, mass. The more mass it has, the harder it is to bend, and the bigger the circle probably. You're going to have to tell me how much charge it has. How will the amount of charge affect the size of the circle? The magnetic field can get a lot better grip on things that have a lot of charge and yank them really hard. The stronger the magnetic field, the bigger the grip. This becomes a 1. What about V? Now V is a little interesting. If you fired at a faster speed, fired 2 particles here, well, how will the size of their circles compare? And of course, you can just solve this for radius, basically. But it's not quite so clear because the faster moving guy feels a stronger force because this force is proportional to the velocity vector. But the faster moving guy is kind of harder to bend, harder to curve. But this one comes into the V squared and this is V. So overall, we kind of put this together. MV squared over R is kind of Q. I'm going to try to be really thorough and put the absolute value on the Q, but if I don't, it's always supposed to be there. And then what do you get if you solve for R, let's say solve for R. So we lose a factor of V, and let's just say radius turns out to be MV over QB. And this is the radius of the circular path. Does that work? I think that works. Faster guys are going to be bigger paths because they feel stronger forces, but they're much, much harder to bend or something like that. And if you wanted to make this slightly more general, we started with the situation where V started out perpendicular to the green vectors. If you want to make it slightly more general, you might make this R equals M times V perpendicular over QB. And what might I mean by V perpendicular? I only want the component of the velocity perpendicular to the green magnetic field. Because what happens to a component of the velocity parallel to the green magnetic field? It doesn't feel a force. So, so this would mean component of V perpendicular to magnetic field. And basically what's going to happen in terms of, I've kind of taken the absolute value of the charge here. What about directions? All the positive stuff is going to circulate one way, and any negative charge placed there will circulate the other way. The radius of the circle might be the same, but kind of like the sign of the radius or something like that, the orientation is flipped. What happens if you put something there with no charge and fire it to the right? Just goes at a nice steady speed to the right. So like all the positive stuff is going to circulate, let's say that's clockwise. All the negative stuff is going to circulate counterclockwise of various size circles if you kind of redid this experiment over and over and over with different charges and different masses. What's another question you might want to answer? What's another thing you might be curious to know about this motion? How big is it? Well, we got kind of an answer here. What else might you be curious to know? How long is this circle? How long will it take you around the circle once? How many times do you go around the circle in a second? Tell me about time. So that should be pretty easy to work out where you have a formula for the radius of the circle. What could we do to find the time? I'm going to kind of find the time. What about period? Sorry, period would be, and this is kind of interesting. How long will it take to go around there? Well, the period would be, you know, the distance over the speed. The distance for one orbit divided by the speed at which you're moving along the orbit. Well, what's the distance? 2 pi r, and the speed is v. And we have the formula for r, so let's pop that in there. So it's 2 pi over v, mv over qb. And something kind of interesting happens here. What happens to the v's? What happens to the v's? I think they canceled out. So the time to go around would be 2 pi m over qb. And that's period. Radius. And if you take the reciprocal of that, you can call it frequency. The frequency depends on the type of object, Q and M, and how strong the magnetic field is, but it doesn't depend on how fast you're going. And that's kind of, it's true. I'll write the reciprocal here. F is reciprocal of T. This should have units of time or seconds if you popped in the units appropriately. And then QB over 2 pi M frequency, you know, in like hertz. This is period in seconds. So this is often called the cyclotron frequency. A cyclotron is a device that's kind of built to try to take advantage of the fact that this does not depend on the velocity. So we might talk of velocity, angular velocity. You could do that as well. How would you turn this into an angular velocity? Angular velocity is usually omega, and it's 2 pi times f. So if you multiply this by 2 pi, that would cancel this 2 pi. And you'd say the angular velocity is qb over m, or the angular frequency would be another term, qb over m, frequency, qb over 2 pi m. So here's how people take advantage of the fact that this doesn't depend on velocity. Let's say you have a charged particle and you want to get it going pretty fast. You want to get it going. So your job is to accelerate the charged particle. You want to get it going pretty as fast as you can. It would be kind of like this. It'd be kind of like, let's say you had a ball just hanging, just free, just one ball kind of that you could pick up and throw. And you have another ball that's like on, kind of like tether ball. It's on a tether to a post. Which ball can I probably get going faster if I can do anything I want with it? The ball that is not touching anything, or the ball in the tether to the post? Well, kind of the idea is if I pick up the one ball, I can only accelerate it for a while, then I kind of got to like let it go. So I can give it some energy, but I only get kind of one shot at giving it the energy. But if the ball's on the post, what could I do? Or the kid on the swing, what can I do? Give you a little bit of energy and wait for you to come back, give you a little bit more, give you a little bit more, give you a little bit more. And this is kind of like the kid on the swing, because do you have to change the rate of your pushing as the swinger speeds up? No, it's the same rate for the small swings, for the medium swings, and for the big swings. So you don't even have to pay attention. You just kind of like close your eyes and kind of push. And if you get at the right rate that matches the rate of the pendulum, then you'll be dumping energy and kind of continuously, and you get several passes at it. So you don't have to kind of be incredibly powerful to build up a large energy transfer. So how will that kind of play out here? Instead of the thing going and coming back, swinging forward and backwards, it's going around a circle and you give it a kick. So every time it goes around the circle, you just kind of wait for it to come around and you give it a kick. And what happens the next time? It goes around a bigger circle, but it takes the same time to go around the bigger circle at the high speed as it went around the medium-sized circle at the low speed. So you just kind of sit here giving taps at a regular rate, and it'll speed the object up until it's following a really big circle. And what's going to limit your ability? Will anything limit how fast you can get the object going? kind of conceptually, nothing would kind of limit it, but it's got to follow a larger and larger circular path, which means you have to have your magnetic field be uniform over a larger and larger region of space. So it's kind of ends up being limited by how big, either strong, but also physically large your magnet is. If your magnet only kind of provides you with this 3 Tesla field over a 10 centimeter region of space, that's kind of like limiting your max radius. And if it's limiting your max radius, it's going to limit your max velocity for a given mass and charge. So these are a couple of things. And the word cyclotron will go around along with all this. So I think I'm going to say one last thing and kind of leave it there. Which question got into this? Which homework question got into this stuff? It gave you some data about different ions or different atoms, I think. And it said a nitrogen atom has a certain mass, carbon and oxygen have certain masses. And then it kind of asked you to calculate to, I think, a pretty high degree of precision with several digits, right? Let's calculate the cyclotron frequency for 2 different objects. So a different Q and M pair, maybe the same Q, but different M's, I think. Different QM pair for 2 different objects that might be circulating in the same background field. So we had V, which was the same for the 2. I think they happen to have the same charge. They were both like +1 ions or -1, or can't remember the numbers. One was CO, carbon and oxygen, and one was N2. Is that right? And yeah, N2 plus, so charge is +1 E for the first guy, charge is also +1 E for the next guy. What's part A? There is no part A? Okay, started with B and C if I'm reading that right. O2 plus, sorry, O2 plus, also +1. Which of these have very similar masses? None of them are, they're all kind of the same, but which one has very similar masses?
N2 and CO.
Yeah, to roughly, if you look up N2 and you don't care about the precision, it's like 14. 2 14s is 28, and C is 12, and O is 16, so it's about 28. But it's not exactly 14, exactly, actually the 12 is exact. It's kind of the way we define atomic mass units. But this sum is slightly under 28, and double of 14 is slightly over, double the middle one slightly over 28. So if you keep a lot of precisions, the circulating rate is a bit different. And the lighter one, which one's the lighter one? CO is slightly lighter, lower mass. The lighter one will probably go around the circle a little bit more quickly, higher frequency, take less time. And the rest of this is just kind of talking about the digits it wants you to use to get the level of precision desired to distinguish, especially the answer to part B to the answer to part C. They would also go around larger circles or different size circles. Okay, so last thing I want to say is this. What about the 3D version of this? What if instead of firing the velocity, the particle straight to the right, what if you fired it a little bit to the right, but a little bit at us? So let's say I give it this component in the plane of the page, but I also give it a slight out of the page component. So the initial launch of the velocity is kind of like that. What will that particle do? It's actually really easy to break this velocity into the 2 components that are easy to deal with. So I'm giving it a horizontal component just like the one here. So what's going to happen in the plane of the page? This object's going to kind of circulate around, but I'm also giving it that I wasn't previously giving it. I'm giving it a component of velocity at me. What will that component, what will happen to the slight, let's say, out of the page velocity component if there had been one at the start? The magnetic force will never point out of the page or into the page. So if you give something a tap out of the page, what will happen to it? It just drifts out of the page at a nice steady velocity because that component of velocity never experiences an acceleration. So what's the overall motion of the particle if I start it to the right at the mass a little bit? What's the overall motion? It's a circle in the plane of the page, but you just drift that circle this way, so you get what might you call that? That's what you get.
Spiral.
You get a spiral, you get a helix. It spirals around, and now you can almost imagine these green dots as like wires. It spirals around the magnetic field lines. And if you give it a tap along the magnetic field lines, it'll just drift along them, but spiral, and all the positive stuff will spiral one way as it drifts towards us, and all the negative stuff will drift towards us, but spiral the other way. If the magnetic field lines curve around, the spirals will kind of curve to follow the magnetic field lines. And the easiest question would be this: how fast will the charged particle be moving 8 seconds later? Same as the speed at the start. If magnetic forces are the only ones affecting a charged particle, the direction, the time, the size, those could be interesting questions that take the details to calculate, but the speed's never going to change. We sometimes say things like magnetic fields do no work on moving charges. So what does that mean? They don't change the energy. In particular, they don't change the kinetic energy of the moving charge. They might change the direction of the velocity vector, but not the magnitude, which is what kinetic energy cares about. All right, there we go. Spiraling, yeah, and you can see some references to that, and maybe we'll look at some pictures of what happens when a charged particle gets kind of caught in the Earth's magnetic field and does stuff. The northern lights, that's what happens, or might happen.
Aren't the northern lights supposed to pop up sometimes?
I haven't heard that, but I wouldn't be too surprised. I mean,
There was like a date or something that's.
Okay. I mean, there's kind of like cycles in the life of the sun where it's a little more active and a little less active, and that tracks with the northern lights. So if we're approaching one of those higher activity times, that's somewhat predictable.
Thanks.
Yes.
Don't have the stapler, so I'll just.
You can give it to me. I'll just staple it downstairs when I get there, which won't be in too long.
Sure.
Yep, that's pretty common.
This is Friday.
Zach and Rockford. Here.